Okay, the instant before it touches the floor, I'm going to call that ground level. Okay, so it doesn't have any more distance to fall. Okay, we've got to where it's just infinitesimally close to the ground. It's at y equals 0. What has happened now? Because the force of gravity has still been acting. It's an internal force. Where is it stored now?
Almost all of it in kinetic energy.
All of it is kinetic. Okay, so when it
Wait, I thought
lands,
kinetic had to have a velocity.
at the instant, right before it impacts,
Okay.
it'll be moving its fastest.
Did you say all of it?
All the energy. Because we haven't compressed anything.
No, but I mean, there's still gravity on it.
That's a force, though. But it doesn't have anywhere else to fall. So
So the energy of gravity.
it only has
Doesn't
gravitational
rely-
potential energy if it could fall, if it's above,
Oh,
if
right,
it's above
potential.
the ground. Yeah, I think you're confusing the force and the energy. Gravitational potential energy is when two masses are separated, but the force, it can have that even if they're not separated. It still has the force. So we have kinetic energy. So all these circles are the same size because the total energy is constant. Okay, and it was an internal force that caused the storage modes to change. Okay, part B, the little car. Oh, one more circle we should draw here. At A, what energy did it have? We should draw the pie chart for A. Well, it didn't have any gravitational potential because it was on the ground. It didn't have any kinetic because it wasn't moving. It didn't have any elastic potential because nothing was stretched. And it's the beginning of the problem, so we're going to count that as our 0 level for internal energy. So it had no energy, so the pie chart is just a dot.
It had future energy.
Yeah, what?
Future energy.
Say it again.
Future energy.
Future energy. That's only because I was nearby. I had the energy. If you wonder where the energy came from outside the system, it was from my breakfast. Okay, part B. So the car is at its lowest level right here. How much energy does it have?
0.
0. So a dot. So at A, the pie chart is just a dot. And then at B, it's all kinetic. And I don't think your paper says what's happening at C and D, so I think I have to tell you. At C,
Well, it starts decelerating from friction.
yeah, C,
Starts
it's moving, but it's
Starts
slowing
accelerating.
down.
Decelerating.
So-
Same thing.
So would that pie chart be smaller?
Oh, good question. Would that pie chart be smaller? So what we have to ask ourselves is, are there any external forces acting between here and here that could take energy out of the system?
No.
No.
Well, let's think. What forces are there?
It's friction.
Friction. There's friction.
Friction from the ground. From
Is
the floor.
friction external?
'Cause
So
it's-
let's see. It's between the cart and the ground or the floor. Is the floor part of the system?
Yes.
Yes. So friction is internal.
Okay.
Yeah, and I know with momentum we didn't put friction in the system. For energy, we will usually include the ground or the surface in our system. Okay, so we don't have any external forces, so the total energy is the same. So how is it stored here? So the circle should be the same size. Is there gravitational potential energy?
No.
No. Is there kinetic energy?
Yes.
Yes. How about compared to here? The same amount or less?
Less.
Less because it's slowing down. So less kinetic energy. So, okay. Is there elastic potential?
No.
Nope. Is there internal energy?
No.
Ah.
Unless
What happens when friction occurs?
Creates heat.
It causes those molecules to vibrate more inside the surfaces. So friction is a force inside the system. What it does is it causes energy to convert into this other storage mode of internal energy. So we have internal energy because of the friction. The friction, if you rub your hands together, right, they get hot. Okay, that's because you're increasing the motion of the molecules in your hand,
Oh no.
increasing the internal energy. And then at D, the cart has completely come to a stop. Does that mean it has no energy? The system?
Well, now
Doesn't
it's,
it?
Where did the energy go?
now it's supposed to have more internal energy from when it was slowing down. So now
Yeah.
it'll do more now, I guess.
Yep.
Oh,
The longer
Really?
it slides, right, where did the energy go? It all went into making the molecules of the surface and the car move
I
faster.
would think that the air from room temperature would kind of cool it back down.
There might not be any air.
I didn't include the air.
We're assuming a lot of things.
And that's the key,
Okay.
right? That's what makes physics tricky, I think, is to figure out what are we assuming and which things matter. And these circles should all be the same size. I apologize for my drawings, which
So in
all look
space,
the same
in
size.
space, is there not any molecule in the air?
Well, not necessarily, because there's like all kinds of debris flying around out there.
But like there's
Way out!
it doesn't like make up the air the way it does
There's
on
no,
Earth.
right, there's not, no. Yeah,
So
there's
then
no.
is there friction? Like would there be
No.
any
mm-mm.
internal energy? There isn't.
That's why when the, like, for the spacecraft or the shuttle and all that, you know, when they go out, a really dangerous part is when they go through the atmosphere.
Mhm.
Because they get so hot from all that friction with the air, but once they're out, they don't continue to have all that heating up of the sides of the space.
But there's also no way to transfer the energy. Then is there? Because it can't transfer out of the system after you're into a place where there's nothing around you.
Well, you can radiate heat.
So you can radiate
You can
energy.
still radiate energy away.
Also, can you like use a flashlight or something to get a bunch of light energy to leave your spaceship?
Yep, if you shine light out, absolutely. Yeah. Okay, so then part C, let's do the last one. Okay, we've got the cup of water. So at room temperature, we're going to say that was 0 internal energy, however much it had at that point. That's our 0 level. This is the mug in part D. And then we heated it up in the microwave. And what's in our system in this one? We need to be clear about what's in the system.
The cup,
Cup, water,
is
air, surface.
The cup, the
air
water,
is-
the air.
So this
and the
time it'll
surface.
cool down.
So when this cools down, where's that energy going?
It's radiating
cup
out.
in the air.
It's going into the cup and
The
into
air.
the air. Are those things part of the system?
Mm-hmm.
Yeah, of course. Cup.
All of them?
Mm-hmm.
Yep. So did the system energy change?
No.
From B to C.
From B to C, it did not change. It went into a different place. So here it was mostly these molecules in here that were moving fast. Now here we've got air molecules moving fast. Faster than they were. But that's all part of our system. So it just changed object location, but it's still there in the system. Now if the air was not part of the system, then what would this picture look like? What if the system was just the mug and the water?
It wouldn't have
Smaller
any
circle.
energy afterwards.
Then if it has cooled down to this point, you'd be back to just drawing a dot. If it had only cooled part way, then you would draw a smaller circle to show that there's less energy in the system. Okay.
Mm-hmm.
Okay, a bazillion details. I think we are ready now to do our, I'm going to do one example with you and then I'll let you go do some. Number 7 is just a review. We've already been drawing energy pie charts. The size of the circle represents how much energy is in the system. The size of a wedge represents the amount of energy in that storage mode.